Hello all, welcome to the next lecture of network analysis and synthesis. We are discussing the fifth unit, which is the network synthesis. So, in the previous lecture, we have studied that whenever we want to do the network synthesis, the input that we need to take is a network function. And basically, if we cannot synthesize every network function. So, if a network function is to be synthesized, then the necessary and sufficient condition that it's to be satisfied is that it should be a positive real function. So we discussed when we can call a network function as a positive real function. So it has to satisfy three conditions. The first condition is the denominator of the network function should be Horvitz polynomial. Second condition says that all the coefficients of the network function, that is both in numerator and denominator, all the coefficients must be positive. And the third condition it has to satisfy is that the value of h of s, that is the real value of h of j omega, should be greater than 0 for every s is equal to j omega, for every j omega value. Okay, so right, we have seen how we can test the particular network function using these three conditions. Okay, so in theory, now let us take one example, right, and let us check or see the mechanism of testing this network function. Okay, so I have taken a simple example. So this z of s is equal to, right, s cube plus 4s square plus 7s plus 3 is the numerator, and s cube plus 3s square plus 5s plus 6 is the denominator. Okay, so the first condition is, so if we have to say that this is a positive real function, okay, so we are testing whether it is a positive real function or not. So the first condition that we need to check is the denominator polynomial must be Horvitz. Okay, so it has to be a Horvitz polynomial. So how can we test it? Simple. So here let us take the denominator polynomial, which is q of s. Let us call this as q of s is equal to s cube plus 3s square plus 5s plus 6. Okay, so there are three conditions which has to be satisfied to call this polynomial as a Horvitz polynomial. Okay, so first condition is all the coefficients must be positive. Yes, it is, all of them are positive. Okay, and none of the terms should miss from the highest power to the lowest power. So highest power is s cube, lowest power is s power 0, so all the terms are present. Okay, and the third condition is when I divide this into two parts, okay, even polynomial and odd polynomial. Okay, so I will get 3s square plus 6. So this is my even polynomial and this is my odd polynomial. So now when we perform the successive division of odd to even polynomials, the quotients should all be positive. Okay, yeah, let us do this. Okay, so yeah, so here I have to cancel out the s cube term. So therefore the first I have to multiply this with right, I have a 3 here, so that I have to get cancelled out, so s by 3. So when I do that, so what is that I'm going to get? 3s square into s by 3 will give me s cube. Okay, 6 into s, 6s by 3, so 6s by 3 is 2s. Okay, isn't it? So this is what I'm going to get. Okay, right, so s cube gets cancelled. 5s minus 2s is 3s. Okay, right. Next, now take this remainder will be taken as the divisor and this will be taken as the dividend. So 3s square plus 6. Okay, yeah, so so I have 3s here, I have to get cancelled out 3s square, so I'll have to multiply this with s, so this will give me 3s square. So this gets cancelled, so I get 6 here. Okay, yeah, so we can stop here or we can make the remainder to 0. Okay, yeah, so what is the next thing? So I have 6 here, I have 3s here, so what is that I need to do? I need to multiply this by s by 2. Okay, so if I multiply this with s by 2, then I'll get 3s, so which will be get cancelled out and the remainder will be 0. Okay, yeah, so here we can see that, right, all the quotients that I got, s by 3, s and s by 2 are all, right, positive. Okay, so that is the necessary condition to call this polynomial as a Horvitz polynomial. So all the coefficients are positive, all the terms are present, and when I divide, right, even part by odd part, I'm getting all the quotients as positive. So we can say that this polynomial is a Horvitz polynomial. So we got the first condition. So the first condition is satisfied. The first condition is okay. So the condition one is the denominator must be a Horvitz polynomial. Okay, so that is satisfied. Second condition. What is the second condition? It's a very simple condition. So all the coefficients in the numerator and denominator must be positive. So all the coefficients are positive. Okay, so no problem. This is also satisfied. Okay, now okay, so that condition 2 is also satisfied. Therefore we can say that this h of s will be right real. H of s will be real for all s real. Okay, so if I substitute the real value of s, then h of s will also be real. So that is the second condition, which is also satisfied. Now the third condition we need to check is, so real part of h of j omega should be greater than 0 for all, right, s is equal to j omega. Okay, so for all values of h of s equal to j omega, the real part of h of j omega should be greater than 0. So this condition has to be satisfied. Now for checking this, we can do it in another way. So the condition that we can check is m1 of s into m2 of s minus n1 of s into n2 of s is right at s is equal to j omega, at s is equal to j omega should be greater than 0. So instead of checking this condition, okay, we can verify this condition, right, and we can conclude from that. Okay, yeah. So let us verify this condition. So what is this thing here? So here m1 of s is the right even polynomial of the numerator. So that is 4s square plus 3. Okay, and m2 of s is the even polynomial of the denominator, that is 3s square plus 6. Okay, right, now let us multiply this. M1 of s into m2 of s is equal to 4s square plus 3 into 3s square plus 6. Correct? So this will give us 4s square into 3s square is 12s power 4. Okay, so 4s square into 6 is 24s square plus 3 into 3 is 9s square plus 18. So this can also be written as 12s power 4 plus 24 plus 9 is 33. So 33s square plus 18. Okay, correct? Yeah. So this is m1 of s into m2 of s. Okay, yeah. So let me write it here. m1 of s into m2 of s is equal to, so 12s power 4 plus 33s square plus 18. Okay, right. Now next n1 of s into n2 of s. n1 of s into n2 of s. So what is n1 of s? n1 of s is the odd polynomial of the numerator. What is odd polynomial of the numerator? S cube plus 7s. Okay, n2 of s. What is n2 of s? Odd polynomial of the denominator. So that is s cube plus 5s. Okay, yeah. So when I multiply these two, s cube plus 7s into s cube plus 5s. Okay, yeah. So this is equal to s cube into s cube, right, is s power 6. Okay, plus s cube into 5s, so 5s power 4, 7s into s cube, so 7s power 4 plus, okay, last term. So what is the last term? 5 into 7 is 35s square. Okay, yeah. So when I multiply these two polynomials, I'm going to get this thing. So this is equal to s power 6 plus 5 into 5 plus 7 is 12, 12s power 4 plus 35 s square. Okay, yeah. So this is the right n1 of s into n2 of s. Okay, yeah. Now from this right, from this the condition that we need is this one, m1 of s minus n2 of s. So m1 of s is 12s power 4 plus 33s square plus 18 minus, okay, so n1 of s into n2 of s, so that is s power 6 plus 12s power 4 plus 35s square. So this is equal to, right, this is equal to So I have 12s power 4 minus 12s power 4 gets cancelled. So minus s power 6. Okay. 33s square minus 35s square minus 2s square. Okay. Plus 18. Correct. Okay. Now this is the term m1 of s into m2 of s minus n1 of s into n2 of s. Now we need to check. We need to substitute s is equal to j omega. Let us substitute s is equal to j omega. So when I substitute s is equal to j omega, so what I am going to get, m1 of s into m2 of s minus n1 of s into n2 of s at s is equal to j omega, is equal to, okay, so minus j omega whole power 6 minus j omega, sorry, yeah, minus j omega whole power 6 minus j omega whole square plus 18. Okay, yeah, so this implies this is equal to minus j power 6 into omega power 6 minus j square into omega square plus 18. Now now this implies, so what is minus j power 6 minus j minus 1 into j square can be written as minus 1 whole power 4, which is basically, right, minus 1 itself. Okay, yeah, so j square is again minus 1, so j square, so minus 1, so minus 1 into minus 1 is basically, right, we can write this as, okay, j square is minus 1, so minus 1 whole square, or sorry, j square is minus 1, so minus into minus is plus, so omega square plus 18. So this is also, right, yeah, just a second, this is equal, so this will become minus 1 into minus 1 whole power, right, omega power 6, right, and this will be omega square plus 18. So we can write omega power 6 plus omega square plus 18, which is a positive quantity. Okay, so it is a positive value, so therefore we can say that this m1 of s into m2 of s minus n1 of s into n2 of s is a positive value. So our given, right, condition, third condition, is also satisfied. Therefore I can say that the given function, h of s function, whatever we have been given in the problem, it is a positive real function. It is satisfying all the three conditions. Okay, so in this way we can check for any given network function whether it is a positive real function or not, we can verify. So once if a network function is satisfying the condition that it is a positive real function, then we can do the network synthesis. Okay, so how we can do the network synthesis, we will discuss in the upcoming lecture.